Hey everyone, you know the periodic table of elements, right? Of course you do. It's this absolute icon of science. It's in pretty much every classroom, every lab. We all know that shape. But have you ever, really stopped and asked yourself why it has that shape? Why this specific, kind of funky layout? Well, that's what we're going to dig into.
I mean, it is a little weird looking, isn't it? It's not a nice, simple grid. You've got those two columns way over on the left, this big block in the middle, and that other block that looks like it's just floating at the bottom. Why not a clean rectangle? Well, I'll tell you this, that shape is not an accident. It's not a design choice. It's a map. And today, we're going to figure out how to read it.
And the cool thing is, the reason behind this whole structure isn't some super complicated mind-bending formula. It's actually this beautiful, elegant story about the basic rules that run our entire universe. And trust me, once you see it, you will never look at this chart the same way again.
So, to get this, we've got to go back a bit, back to the 19th century. You had all these chemists who kind of felt like detectives. They had this growing list of elements, right? And each one had its own unique personality, its own properties. They were just convinced there was some kind of hidden code, a pattern that tied them all together. They just had to crack it.
And slowly, they started finding clues. Back in 1829, a guy named Johann Dobreiner saw that some elements came in these little groups of three, or triads. Then, fast forward to 1865, John Newlands came up with his law of octaves, noticing that properties seemed to repeat every eighth element, kind of like notes on a musical scale. They were getting warmer, you know? But the big one, the big breakthrough was just around the corner.
And here's what set the next step apart. It's the difference between just organizing what you have and actually predicting what you don't. See, the early models were just describing what was already known. But in 1869, Dmitri Mendeleev, wow, he created a table that could basically see into the future. He arranged the elements by their atomic mass and saw the repeating patterns so clearly that he actually left gaps in his table for elements that hadn't even been discovered yet. And guess what? He was right.
And this really gets to the heart of it. Mendeleev had cracked the code. He found the what, this incredible rhythmic pattern to the elements, but nobody, not even him, had any idea why. The why was still a complete black box.
So that brings us right back to our big question. Mendeleev's table was a game changer, for sure, but the modern table we use has a standard 18 columns, or groups. Why that number? What fundamental law of nature says it has to be exactly 18? Well, it turns out the answer wasn't something they could find in a lab. It was deep inside the atom itself.
The missing piece of this whole puzzle? The electron. It wasn't even discovered until decades after Mendeleev's work, but this tiny little particle held the key to everything. See, the way electrons are arranged inside an atom dictates its entire personality, how big it is, how it reacts, everything. The secret code that builds the periodic table is written by electrons.
Okay, so to get this, let's think of an atom like a really strange apartment building. Right in the middle, you've got the nucleus. And the electrons, they live on different floors of this building. Scientists call them shells. The first floor is really close to the center. The second is a little further out. The third is even further, and so on. Makes sense, right? Now let's zoom in a little. Each floor, each shell, is divided up into different kinds of apartments, or subshells. Now, it gets a little more complicated, but for what we're doing today, we only need to know about three types of apartments: the S apartment, the P apartment, and the D apartment. This is where the magic really starts to happen. And this, right here, is the most important rule in this whole story. Each type of apartment has a strict, non-negotiable capacity. An S subshell can only hold 2 electrons. That's it. A P subshell can hold 6, and a D subshell can hold 10. You have to remember these 3 numbers: 2, 6, and 10. I'm serious. These numbers are the entire reason the periodic table looks the way it does. Okay, one last piece of the puzzle: valence electrons. These are the electrons living on the top floor of our atomic apartment building, the outermost shell. These are the socialites. They're the ones on the frontier, the ones that meet other atoms, form bonds, and make all the chemical reactions happen. An atom's entire chemical personality comes down to these valence electrons. Okay, you're with me? We've got our rules, we have the apartment building, we have the different rooms, and we have their strict capacity limits. We now have everything, literally everything, we need to build the periodic table from the ground up and finally solve this mystery. So, think about moving across a row of the table. What we're really doing is filling up these electron apartments in a specific order. First up, we fill the S subshell. Since it can only hold 2 electrons, boom, that gives us the first 2 columns of the table. Next, we filled the D subshell. That one holds 10 electrons, which gives us that big 10-column block in the middle. And finally, we fill up the P subshell. It holds 6 electrons, giving us the last 6 columns on the right.
See how it works? The logic is it's perfect. The number of groups in each block of the table matches up exactly with the max number of electrons that subshell can hold. 2 electrons for the S block means 2 groups. 10 for the D block gives you 10 groups. 6 for the P block, 6 groups. It's not random at all. It's just simple math.
So, what happens when we put it all together? You take the 2 groups from the S block, plus the 10 groups from the D block, plus the 6 groups from the P block.
18. Boom. There it is. The reason the periodic table has 18 groups is a direct, unavoidable consequence of the laws of quantum mechanics, the rules that say how many electrons can fit into S, P, and D orbitals. It's not a design, it's a fundamental property of matter.
And this structure explains everything about how elements behave. The elements in group 1, like sodium, they have just one lonely valence electron, which makes them super eager to react. Group 17, the halogens, like chlorine, they have 7, so they're desperately trying to grab just one more. And the noble gases way over in group 18, their outer shells are totally full. They're stable, they're satisfied, they don't want to react with anything. It all just clicks into place.
So, we solved the puzzle. But understanding this hidden logic isn't just about a cool bit of science history, it's about unlocking the incredible power this table gives us to shape our future.
Because once we understand these underlying rules, the periodic table stops being just a list of stuff. It becomes, well, it's like a crystal ball for chemists. If you tell me an element's position on the table, I can predict its properties, how it's going to behave, and what we might be able to do with it, without even running a single experiment.
And that predictive power is the foundation of so much modern science. It's how engineers can design new materials for smartphones and jets. It's how chemists can design life-saving medicines by figuring out how different molecules will fit together. It's the ultimate cheat sheet for anyone who works with matter.
And that really is the beauty of it, isn't it? The table isn't some static museum piece that just catalogs the past. It's a dynamic, living map that guides us toward the future. It shows us what's possible. It's a tool for pure invention.
So as of today, we know of 118 elements, and they all have a perfect home on the table. The 7th row, our 7th apartment floor, is completely full. But you know scientists, they're already hard at work trying to create element 119, which would be the very first element on a brand new 8th row. And because of the table's logic, we can already make some pretty good guesses about its properties. But what secrets will it really unlock? Well, that's a question for the next generation of explorers to answer. Thanks for joining me.